So let's move on to Theorem 6.7, which is Mobius inversion formula. Let f and small letter f be the two number theoretic functions related with the formula f of n is equal to the summation of f of d such as d divides n. It's also converted into f of n is equals to the summation of mu of d, f is to n over d, such as d divides n, and equals to summation of mu n over d and f of d, which is d divides n. So, reminder that mu of d is a divisor and the n over d is a divisor also, and equals of summation of the mu equals n over d. N over d is also a divisor, and f d is also a divisor. The example is n is equals to d is to d prime. D over n, which is d divides n. So d prime over n, which is d prime, is equals to n over d. If the capital F is a multiplicative, then so the small f is also a multiplicative. We have to prove that n is equals to d into d prime. So d prime is equals to n over d. Consider that d is the divisor of d over n, and the d prime is also a divisor of n. Prove that the two sums mentioned in the conclusion of the theorem are seen to be the same upon replacing the dummy index d by d prime is equals to n over d. As d ranges over all positive divisors of n, so does d prime. We get the summation of mu of d f over n over d, such that d divides n is equals to summation of mu of d summation of mu over d, such as d over n, and summation of f over c, such as c divides n over d. So in summation of f of c, we have f over n over d, we have to substitute summation of f of c. So it equals to summation of d over n times the summation of mu of d and f of c, such as c divides n over d. Simplifies to the summation of f of c times the summation of mu of d, such as d divides n over c, is equals to the summation of f of c times 1, which is equals to f of n. This has the giving as the stated result. So let us use this example. N is equals to 10, again, to illustrate how the double sum equation is turned around. In this instance, we find that our n is equals to 10, which is the summation of f of c times the mu of d, such as d divides 10 over c. To see how the Mobius inversion formula works in a particular case, we remind the reader that the functions r and a may both be described as sum functions, which is tau of n is equals to summation of 1, which is d divides n. Turning the situation around, one might ask whether the multiplicative nature of the capital letter F focuses that of small letter f. So surprisingly enough, this is exactly what happens, which is if capital letter F is a multiplicative function, and so the f of n is equals to the summation of f of d such that d divides n. Then the small letter f is also a multiplicative. Rule. Let us prove that let m and n be relatively prime positive integers. We recall that any divisor d of m and n, m times n, can be uniquely written as d equals d1 times d2, where d ln d2 ln and the GCD sa d1 and d2 is 1. So we will use the inversion formula, which is the f of n is equals to the summation of mu of d and f of m and n over d such that d divides m and n. So it will come up with f of n f and f of n. So it also the same. This is which is the assertion of the theorem. Needless to say, the multiplicative character of mu and of the capital letter F is crucial to the previous calculation, for n is greater than or equal to 1. M of n is equal to the summation of mu of k, as k is equal to 1 to n. Then m of n is the difference between the number of square free positive integers k is less than or equal to n, with an even number of prime factors and those with an odd number of prime factors. For example, our m is 9, so it is equals to 2 minus 4 is equals to negative 2. So in 1987, Franz Merters of 1840 to 1927 published a paper with a 50-page table of values of m of n for n is equals to 1, 2, up to 10,000. On the basis of the tabular evidence, Mertens concluded that the inequality of the absolute value of m of n is less than the square root of n. So our n is greater than 1. Is very probable. In the previous example, which is the absolute value of m of 9 is equals to 2 less than the square root of 9. So these conclusions later become known as the Mertens conjecture. A computer search carried out in the 1963 verified the conjecture of all n up to 10 billion. But in 1984, Andrew Odlyzko and Hermann Terrell showed that the Mertens conjecture is false. Their proof, which involved the use of a computer, was indirect and produced no specific value of n for which the absolute value of m of n is greater than or equal to the square root of n. All it demonstrated was that such a number n must exist somewhere. Subsequently, it has been shown that there is a counterexample to the Mertens conjecture for at least one of n is less than or equal to 3.21 times 10 to the power of 64.